Yeah, and so I think the primary point of this presentation here is, like it says, we're using the graph to preserve historical data and enable EIP-44s. And so I think the thing that I really want to do is start kind of engaging the community. Like we just heard on the panel here, there's some interest here in just trying to make the right connections with the right people to really try to put this idea forward. And so whenever I talk about this idea here, it really is, it's a proposal, right? Like a proposed solution, not like the proposed solution for enabling EIP-44s. And so when we talk about preserving historical data, that historical data can be used a lot of different ways, probably more ways than we know now. And so having these multiple diverse kind of solutions, right? The Portal Network is still developing a solution. If we can enable another solution through the graph, it just kind of increases the space of available data there. And so then just I guess another little note about this work is we actually didn't set out trying to design a solution to EIP-44s. This actually came about from some of the verifiability work that we're doing for the graph. So it's specifically, we're trying to prove that data that's been served by indexers within the graph protocol is correct with some notion of correctness. And we kind of just happen upon this, this solution that looks like it could be useful. So yeah, let's get in. So first, I'll just give an introduction to the graph for those who may not be familiar, give a little bit of the history of the graph, and then kind of some of the technology developments that have kind of enabled what we're talking about in this presentation. So first is just kind of this nice visual that somebody in the community developed to kind of describe what the graph does, at least the V1 version of the graph before this world of data services kicks off. And so up here we have our blockchain, right? And so the blockchain is kind of like a series of transactions and emitted events that are kind of submitted and executed kind of asynchronously. So you got kind of this mess of data up here. And so if you're a DApp developer or maybe a data analyst, you might only care about specific slices of this data. And so if you want to start analyzing this data or you want to start feeding this data to your consumers, the first thing that you got to do is start spinning up some infrastructure to start indexing for the specific data that you care about. And it's going to take a lot of time, a lot of effort that you don't really care about, right? You just want your data and you want to serve it to consumers. So that's what the graph provides, right? So for the graph, you specify exactly the data that you want, and then let the graph's indexers handle all of the back end sorting and filtering and transforming of the data for you. And so looking at just kind of one small layer of abstraction, or removing one layer of abstraction, we can start seeing parallels between the graph's indexing stack and kind of traditional extract, transform, load, ETL data processing pipelines. And so up here we have kind of the V1 version of the graph, so the kind of the subgraphs data service, as we'll call it in the world of data services nomenclature. So for extracting data, essentially indexers pulled archive nodes. So you'd have an Aragon archive node, you send JSON RPC requests for the data that you care about, and then you take that data, you have some assembly script that specifies the required transformations on the data that was specified by the consumer. Then after those transformations have been done, that gets loaded into a PostgreSQL database and made available for querying to consumers via GraphQL queries. Yeah, so ETL pipeline there of V1 of the graph. And so then just where the graph is today, so a lot of major dApps are powered by the graph. So this example here, info.uniswap.org, all this data and these dashboards, all the statistics, they're all derived from data on the graph. And then, yeah, another recent development, several months ago now, the graph surpassed 1 trillion queries. So there's a lot of demand for the services that the graph is providing. And with great demand comes greater demand for performance. And so as people start using the graph and new indexers start spinning up, they're finding that it takes a really long time to start indexing a particular subgraph. And so for again the Uniswap subgraph, using that V1 pipeline where you're querying archive nodes to extract your data, it'd take about 2 months to actually sync that subgraph. So before an indexer could even start serving queries and getting paid, they'd have to spend 2 months of spin-up time to get all the data that they need. And so, the graph is an evolving protocol. We got a bunch of core developers trying to solve these problems and make the graph more performant. So the Streaming Fast team developed a technology that basically took that 2 months syncing time down to 20 hours. And so this core tech is going to be like one of the core pieces that we're talking about here, basically the rest of this presentation. And so to really kind of understand where this new tech kind of fits in and understand the bottlenecks of the previous iterations of the graph, just kind of like show, just kind of block diagrams of what that graph V1 stack actually looks like. So you've got your archive node sitting here. The archive node is, downloading data over the peer-to-peer network, and it's storing all this data in some archive database. And then on the indexer software, the graph node software, the indexer is making JSON RPC requests to this archive node. The archive node is looking up the data and then sending that response back to the indexer. And the indexer makes another request, and so you get a lot of these back and forth RPC requests. The graph node indexer, index mode, performs transformations, loads it into that Postgres database, and then the query mode of the indexer infrastructure basically accepts GraphQL queries from a consumer, translates those into SQL queries, and then executes those queries against that database. So now enter Firehose. This is a technology that was developed by the core development team, Streaming Fast. And so Firehose itself sits like squarely in this extract portion of the data pipeline. And so really what Firehose does is it takes blockchain data and it kind of makes it available in kind of two formats. One is these flat files. So it downloads data from the peer-to-peer network, and then it stores it off in these flat files. And then the data is read from these flat files and streamed to downstream processes in the graph protocol. So just a high-level overview again of kind of what Firehose does and what it enables. The first thing is you get one data model for all of your blockchains. So the graph serves many blockchains, EVM and Ethereum-like and non-Ethereum blockchains. And so you have this, this framework gives you one model to work with. It's a really flexible stack. You can run it on a single server, hosted at your house, or you can run it up on a big enterprise scale cluster. The data that is extracted from the blockchain is stored in Google Protocol, serialized Google Protocol buffers, and we call these flat files. And then, with all things in the graph, the code is open source. You can go find the GitHub, look up the Firehose source. You can start spinning up your own Firehose node, start, participating in the graph network. It's all there. It's all available. And then, like I said, the data that Firehose outputs is it's a stream. It's a pipe of data that is consumed by downstream processes. And so why does Web3 need Firehose? And so basically the core thing is like running blockchain infrastructure is difficult. So if you're, you need to handle reorgs, you need to handle hard forks, upgrades to blockchains. If you're indexing multiple blockchains, different blockchains work in different ways. And so you need to have potentially one-off solutions for each of those chains to handle all that. Chains don't have common APIs, so there's a lot of stuff to worry about here. And the nice thing about Firehose is it basically abstracts all of this for downstream data consumers. Okay, so how do we go from like 2 months of sync time down to 20 hours? The core problem, again, is this, this RPC, these RPC calls to archive nodes. It's not fast enough, right? So this call response, it takes too long, you can't get the data. And so then that's where the solution, flat files, comes in, right? So we'll get into kind of how this data gets extracted and stored in these flat files a little bit more, but that's like the biggest, that's where you get your big bang, right? So you're no longer making JSON RPC requests to a archive node. You're basically extracting and storing these data in these flat files. And then just, if you want to go look at the Firehose source, there's like a handful of binaries that you need to be that you need to look out for. So one, you need an instrumented blockchain node. So this is your execution layer node. And then if your blockchain requires a consensus client, you need a consensus client. And then you need your firehose binary. So these firehose binaries, they're specific to each chain that you're indexing. You know, we've got Ethereum, Cosmos chains, Arweaves, other chains. Yeah. So these are the components of your stack that you need. All right. So we saw the V1 stack. Now this is kind of like the future V stacks, right? So I won't say V2 because this isn't all implemented, but this is kind of like the vision going forward, building off the top of Firehose. So now sitting here in your extraction layer, you've got Firehose, you've got your Firehose-enabled full node. It is extracting data from the blockchain, storing it off of these serialized protobufs, and then it's making available a stream of blocks that can be consumed by downstream services. And like, for example, you can take these blocks and feed it into that original kind of GraphQL data service, or in this vision of world of data services, you can feed it down into like any number of potential data services. And if you want to see an example of that, Sam Green has a talk coming up a little later about bringing, for example, like SQL up as a data service. So he'll go into more detail of like these downstream processes. Okay, so the rest of this talk is going to be focused on how can we use the graph with Firehose to enable EIP-44s. And so in particular, we're really going to be looking at these flat files here. These are what we get really interested about. And so the first thing here, there's this quote that I found whenever I was starting to do my research on like what are people doing on EIP-44s, what does the solution space look like currently. And I like this quote because it kind of like jived with my thinking as well. So a shareable and verifiable archive format is generally considered the first step towards implementing history pruning. So this was a comment by a light client here in this Geth pull request. So what we're going to try to show now is, flat files, they're shareable and they are verifiable. So they kind of like meet this first step towards enabling history pruning. And so shareable, I kind of just think is like a self-evident depiction of the shareability of these flat files. So essentially, all of your blocks that get extracted from the blockchain, they get stored in a binary file in a directory, and that's it. This becomes your source of data now, and so you can share this over any number of mechanisms, right? You can throw it up on BitTorrent, you can host it in Google Drive, which is actually where I got these from. But yeah, so very shareable. So now the question is, how are they verifiable? And so what we actually want to look at is like, if we're talking about verifying these flat files, really what we mean is like, how do we verify the data that's stored in these flat files? And so then, what data is actually stored in these flat files? And so the way that Firehose kind of works under the hood is you have your specially instrumented full node. Really what that means is Firehose is tapping the tracing API output of your full node. So basically, as this full node is performing a full archive sync, so say syncing from Genesis and performing the execution of the transactions, Firehose is basically reading from this tracing API output, and that basically standard out gets written to your flat file. So it's literally just going through copying data as this thing is executing and storing that all off in a flat file. And so this tracing API can be instrumented to give you a bunch of data. And so this is my diagram. I don't know how useful it is, but yeah, I made it, and so I've put it up here. This is all of the data that is available, that is stored in or can be derived from the data stored in flat files. So kind of like at the base here, these are your block bodies and your receipts. So for every block, all of your transactions and all of your receipts get stored in these flat files. From there, you can compute state. The state is not stored in the flat files, but you can compute it from transactions and receipts. The tracing API output gives you access to kind of internal contract calls. And so basically, as you call your smart contract, typically users don't get introspection into the execution internal at smart contract. Well, with the tracing API, you actually see the internal contract calls. And then you can go all the way up to, you can actually get an execution trace, an opcode trace as the EVM is executing. So there's a lot of data. For this talk, really what I care about, because we're talking about EIP-44s, really all we care about is transactions and receipts. This data is here, it's available, it's stored in these flat files. This is what we care about whenever we're talking about the historical data of the blockchain. And so I've made this diagram for multiple purposes, but one of the things that just to kind of like highlight here is I kind of bifurcate this data into like two sections. One, we call it committed data, and the other one is not committed data. And really what we mean by committed data is like, this is the data that gets committed to in your block headers and then is verified by consensus. So again, like your transactions, your receipts, and your block state. Yeah, and then this is a figure that we're probably familiar with in this room. Again, this is how you commit to data, right? So again, we're looking at receipts, we're looking at transactions, and all of these receipts for each block and all of these transactions for each block, these are what gets stored in flat files. Okay, so now, how do we verify flat files? Well, one of the questions that we asked first, okay, how do we verify, why do we want to verify these data in the first place? This was kind of like our starting point as we're working on the graph. Why we started going down this route is flat file. One thing that being able to verify these flat files gives you is it gives indexers the ability to kind of trustlessly share flat files amongst each other, right? So instead of an indexer having to perform a full archive sync of their full node and download the data themselves and then store it off in the flat files, if they can actually just verify the data that's already been stored in the flat file, they can now start sourcing data from peers. And they can basically bootstrap their sync process. Another thing that's really important here, again, like I said, what we're ultimately concerned with in the graph is like, how do we verify the data integrity of data served by the graph? Flat files are the source of all of indexers' data, and so it's basically the source for all downstream data services. And so we need a mechanism to be able to verify that source data is correct. And then the third thing that we our observation, right, is like if we can actually verify all these receipts and these transactions for every block that's stored in all these flat files, then we actually have kind of like a verifiable source of truth for historical Ethereum data, which is where we come and say, hey, we got a potential solution here for EIP-44s. Okay, so how do we verify this data that's been committed in flat files? Here's one approach. It's fairly straightforward. Again, right, like the receipts and transactions are already committed to in the blockchain. They've already been verified by consensus. And so the verification process is pretty straightforward. We decode a flat file, extract all the transactions and all the receipts, and then compute the transaction tree and the receipt tree based off of those receipts, and then compare the roots that we computed to some expected roots from a trusted block header. And so now this trusted block header, this becomes like the big sticking point here. Basically what we mean is it's a block header that the verifier can either trust or they can verify to be part of the canonical blockchain history. So where do we get these trusted block headers? And so really it kind of depends. And really what it depends on is like when did the block occur? Did it occur before the merge or after the merge? And so for block headers before the merge, we actually heard some of the panelists here talking about some of the solutions that people are already working on for handling data pre-merge. So there's interest in the community. Essentially what people are doing is you commit to all of the block headers that occurred before the merge. That data is finalized, right? It's never going to change. So you can generate one commitment, and that commitment will be valid for all of history. And essentially, you commit with like a vector commitment scheme. And then if you want to validate a block header, so you receive a block header, you want to validate, is this block header part of the history? Essentially, the prover would compute an inclusion proof that block header is in that vector commitment. And so there's teams who are doing this. Axiom does something like this. They compute these block hash caches using Merkle trees and Merkle mountain ranges. And then they have some extra sauce that they can, they use a snark to prove that those are computed correctly, and they can do stuff on chain. We don't at this point care about verifying or proving anything on chain. So we actually look at what Portal Network is doing. And Portal Network is using this header accumulator, which it's a double batch Merkle log accumulator. Again, it's another type of vector commitment scheme. And it's basically doing exactly what we want to do, right? Just commits to the block headers, and then it gives you a way to prove that a specific block header was in that commitment. And like I said, it's used by Portal Network. It's also used in these Arrow1 files, which we also heard the panelists talking about a minute ago. So we would align ourselves with the rest of the community here, and we would use these header accumulators. We compute the header accumulators are agnostic to your storage type. So it only depends on the data. So we can compute the exact same values that would be computed by Portal Network would be computed in these Arrow1 files. So that's a good thing here. If we want to look at block headers after the merge, we could also use accumulators. So we could say we take some number of blocks, compute some number of finalized blocks, compute a header, and then do the Merkle proofs. But after the merge, there's actually some additional mechanisms that were incorporated into the protocol, into the Ethereum protocol, that we can use to kind of more trustlessly verify these block headers. One of these is like the beacon chain state. So the beacon chain state actually stores an entire history of block headers in the beacon chain. And so you can, if you have a trusted beacon chain state, then you can extract the block headers from there and then verify transaction and receipt trees relative to those block headers. So that's something like what the ERA files, the ERA, not Arrow1 files are doing. They include this snapshot of this beacon chain state for all of their 8,000 or so blocks. Another feature is this sync committee. So the sync committee was designed for use in light client protocols. It's basically a subset of validators that are appointed every epoch, and their job is to validate block headers and then sign these block headers saying this block header is good. And so right now, just kind of like because of the architecture of the flat files that we have available to us, we're proposing we would use these kind of sync committee signatures to validate our block headers. And here, if you're familiar with the sync committee protocol, you've seen diagrams like this. But basically, the idea is, every epoch there is a randomly selected sync committee, and then that sync committee chooses the next sync committee, generates a signature saying this is the next sync committee. They essentially form this chain of committee members. And so whenever you want to validate a block, you first take this block, and then you have to have a valid sync committee for that block, for that epoch, and check, is this block signed by this sync committee? And so if we want to use this in our infrastructure, essentially what this means is we need to have the validator needs to either have the entire chain of the sync committee, of valid sync committees for kind of the history, over the entire history that they want to validate blocks against. And since we're talking right now about incorporating this into the indexer stack, maybe that's not too big of a deal. We're looking at maybe hundreds of megabytes of data compared to what indexers are typically processing. That's not a lot of overhead. So maybe it's feasible for indexers to extract and store these sync committees for all those blocks. But in other use cases, we might need some other mechanism for proving the validity of sync committees. And so these are things that Kevlar, an ultralight client protocol, is using. They have an optimistic proving system to prove the validity of sync committees. And then you've got SecSync Labs. They're actually snark proving the validity of sync committees and stuff like that. So there's other solutions out there if we needed to use them for other use cases. Basically just kind of where we're at right now. So we're, all the code that we're developing, it's open source. You can find it here. Right now what we have is essentially the code that extracts only the receipts and the transactions from flat files. And then it recomputes the receipt trees and the transaction trees and then compares the roots of those trees to these trusted block headers. Right now those trusted block headers are it's just, our own file of headers. There's no verification going on. That's something that we're currently working on, is developing the processes for computing and verifying the header accumulators for pre-merge data, and then extracting and checking against sync committee signatures for the post-merge data. Right now, recomputing the receipt trees, transaction trees for each block takes about 4.5 seconds on an M1 Mac. Because these blocks are independent of each other, you can imagine you parallelize these things. It's essentially the takeaway is this verification is no longer like a bottleneck for indexers, right? So as indexers are downloading flat files, the bottleneck becomes the download time of a flat file versus the verification time. Okay, so we've talked about flat files. We've shown that they can be shareable. We've shown that they can be verified. And so then now the question is, like, how do we actually ensure that this historical data is retrievable? And so this is where the graph really comes in. And so the graph, it's an incentivized protocol for serving data. And so what we're talking about here is a way of incentivizing flat file distribution, right, and serving historical data. And so I kind of have two arguments here for two arguments here for how this might be done, or why the graph kind of naturally incentivizes this flat file distribution. The first argument is that the graph's current, the V1 subgraph-oriented data service itself incentivizes indexers to preserve and make this historical data available. And it's basically because indexers want to be future-proof. Indexers don't know what consumers are going to be requesting in the future, right? They don't know what subgraphs consumers are going to be specifying. They don't know the range of data that they're going to expect. So an indexer who wants to maximize their profits is going to ensure that they can have this data available so that they can serve subgraphs in the future. And this is also true for other Firehose-based data services. The second argument here is basically part of a world of data services. So again, as we saw earlier in Adam's talk, the graph is really kind of expanding in scope in the type of data that it can provide. And one of those expansions, which is being led by GraphOps, is basically making historic flat files marketable as a data service within the graph protocol. And so essentially what that means now is these flat files themselves will be available basically for purchase for consumers of the graph. So now you can directly download blocks as needed and verify. So thank you. I'm 2 minutes over time. I apologize. I had to try to rush through. We have an ETH research post, and our contact information is there. It's at this link. Like I said, we're really looking at this as a proposal. It's something that we're interested in. We think there's something viable here, so we really love engagement from the people who are interested in this too. Thanks.